Yes. So Mangal and I think we started our research career almost together. Um, I, of course, had finished my master's by 2005, but that was more of a course program. And then we have worked together. We have collaborated in past, and also a lot of exciting work that Mangal's group is doing now. We also follow, and I would like to thank Mangal for giving me this opportunity to give this talk. Um, all right. So with that, I will start my talk. I'll just one sec. All right. Okay, just for the bandwidth, I'm just stopping my video momentarily, and let me just make it full screen. Okay. So the talk that I'm going to give today, the lecture, is on guidance strategies in three-player aerial engagements. So I'll introduce to you the background and the details as we move. And Mangal, just to confirm, we have like 1 hour approximately.
Yes, yes, around 1 hour.
Around 1 hour. So we are already 8:07. So we aim to finish at 9. Is that
No, no, no,
correct?
it's not. Well, the time you start.
Okay. Okay.
Time to
Sorry.
go is 1 hour.
Okay. Okay. Thank you. Um, all right. So now, as you know by the title, that this is about aerial engagements. So let's look at aircraft protection. If you see conventionally, what aircrafts deploy as protection is one is chaff, which is more like a metallic thing that is thrown out, and then it can confuse the radar signal for the presence of the object being detected. The other technology that is widely used is deploying flares, which can confuse heat-seeking missiles. So these are some very conventional methods of luring the missiles away. But we are looking at this problem specifically where uh, an aircraft launches another missile while defending itself from an incoming missile. So as you see on your screen, an active response could be that a defender missile is launched to intercept the incoming missile and and hence avoid the threat. So if you look at this situation, this is an extension of a classical pursuit evasion problem where a missile is trying to intercept a target. But here there are three entities which are involved in this, and the blue team is what um, we will look at. Uh, the point of view from which we look at this problem today in this lecture is the blue team, that is the aircraft, which is hereinafter referred to as target, defender, and missile. So the objective is to develop cooperative guidance laws for the blue team. So this is a problem or a discussion that is not really at the beginning of the guidance theory course that we have here. So I will just very briefly introduce to you the basic ideas of a couple of these guidance laws, and then we'll have to go into the details of this specific problem.
বাজে
So,
কথা বলবি না, মিসাইল কন্ট্রোল সিস্টেম করছি।
all right. So if you look at the basic guidance laws, something that I'm sure most of you who have worked on guidance laws would have heard about is proportional navigation guidance. It is by far the most widely used and popular guidance law, and it also happens to be one of the simplest guidance logics. So on your screen, you see an engagement with the missile trying to intercept a target. Look at this angle lambda, which is the line of sight angle. So that line of sight, the line joining the missile and target, that rotates by lambda dot. And the guidance logic for the missile's heading direction, we are not involved in controlling the speed of the missile. It is only the heading direction, which can be changed by using a lateral acceleration, which is generated by aerodynamic forces. by an acceleration acting normal to the velocity. So that turning rate of the missile is proportional to the rate of change of line of sight angle, and just with a positive constant sitting here. So this is proportional navigation guidance law. And why, you may imagine that why is it that the term navigation sits here? Because as aerospace engineers, we know what's the difference between guidance and navigation. So there's a story behind all this, that when sailors would sail, and if they see another ship uh, on horizon, and then if they see that the ship is getting bigger and bigger and bigger, uh, they they would determine that we are on a collision course, which I will talk about on the next slide. So from these kind of historical perspective, the word navigation has been attached to it, but it is essentially a guidance law, and the only thing here is the positive constant, and that governs the turning rate, which is proportional to the line of sight rate. So that is proportional navigation guidance. Now, how does it work? On top, you see something known as collision triangle. So here the left arrow is for missile velocity vector and the right one is for target. So how do you determine that these two vehicles are going to collide? There are various ways of looking at that. One could be to get the relative velocity. So for example, if you want Vt minus Vm, so you'll have to flip this vector and put it here, and then when you take add the negative vector, that vector would be pointing directly towards the missile. So that means the target's relative velocity with respect to missile is pointing towards the missile. That means it is going to collide. Of course, we are assuming a planar engagement and constant speed vehicles. So from there emerges this idea of collision triangle, where you can see that at a future point, these two points will collide. These two vehicles will collide. So how to construct this collision triangle and see how proportional navigation works on this fundamental principle? So if you look at what I was just now saying, the relative velocity, if you look at missile's velocity here, you can see that right now for the relative velocity components normal to the line of sight to be equal, that is the case when you're on collision triangle. This is not the situation here. The missile velocity vector is not on this dashed line but below that. That means the line joining the missile and the target is rotating in this counterclockwise direction, because the target's velocity component normal to line of sight is greater than the missile's component. So that means in the previous figure, if I go back, this lambda dot is positive. If lambda dot is positive, proportional navigation says that the missile should also point with a positive rate. That means this vector is now being dragged closer to the collision triangle. So that is how proportional navigation works. Now let's look at the other side, where the missile velocity vector is leading the collision course heading. In this case, since the component of missile velocity normal to line of sight is higher, this line joining the two is actually the rate of change is negative. And in this case, proportional navigation would turn this velocity vector towards the dashed line in the clockwise manner, and hence it will always try to bring the missile on the collision triangle which is shown above. So that is why this simple logic works so well, because it has, as you say, catching bull by the horns. So this is exactly the situation here. The line of sight rate is what determines whether two bodies are in collision or not, because if these two velocity vectors normal to the line of sight are equal, which is indeed the case for collision triangle, then the line joining these 2 points will not rotate, it will just shrink. And hence, if the line of sight is rotating, then the missile should change its heading direction uh, using this proportional relation. So that is a background to proportional navigation guidance, and you can see that it is very easy to implement. The information that you need from your seeker is only the line of sight rate, And if you're looking at lateral acceleration, then you'll have to multiply this by the speed, so that should be available by onboard sensors, and hence you can use this guidance law. The second guidance law of interest here is, it is not really driven by the sophistication of the idea itself, but more from a practical point of view. So in the early days, early 20th century, a lot of these missile systems like air to surface, air to ship kind of missiles, they were always, the guidance logic there was that if the missile keeps itself on the line joining the launch platform and the target, then it should eventually intercept the target. So the reason there was that all the sensing capability and all that was not really there on the missile, but actually on the launch platform, and it could communicate that to the missile. So using that kind of a framework, line of sight guidance was used. For example, the first guided missile, air to surface missile, Fritz X, that also used line of sight guidance, but there the pilot themselves could see the line of sight to the ship and then guide. The control of the missile was with the pilot, and they could guide the missile onto the target. So here the uh, idea is that the missile should keep its position on the line joining the launch platform and the target, and by doing so it should eventually intercept the target. So these are two, uh, I would say, pillars of classical guidance theory, that is line of sight guidance and proportional navigation guidance. There is another guidance law that is called pursuit guidance, but that is not of interest to our discussion today. All right. um, Now let us see, let's get back to the problem we were looking at. In this problem, now let's carefully look at this situation. We can certainly assume that the defender has a higher speed and maneuver capability with respect to the target. But if you look at this comparison between an incoming missile and the defender, these are essentially considered to be similar class of vehicles. So a good start to analyzing this problem would be to assume that both these vehicles have identical speed and maneuver capabilities. So that is what we see. This is very unusual of a pursuit evasion problem, because typical missile guidance problems, the target would have much lower speed and maneuver capability. But here, if the defender is trying to intercept this missile, the situation has changed drastically. So so there is no speed advantage, and I'm talking specifically from defender's point of view. There is no speed advantage over the adversary. The maneuver capability is also considered to be identical. One more thing you can note, that this vehicle, missile, is obviously a maneuvering vehicle. It's not a slow moving non-maneuvering target, because this vehicle will carry out maneuvers so as to intercept the target aircraft. So we are essentially looking at intercepting a maneuvering target. And it is possible in certain situations where a very high speed target is intercepted by a lower speed missile, but that is essentially when we are looking at exoatmospheric interception, where we know the trajectory of the incoming vehicle, and the idea is to just come or hinder that path, somehow be on that trajectory. You can be moving with a slower speed, but just because you're on that trajectory, which is more or less known, it is possible to engage high speed targets. But this is not a situation like that. Here the red missile can obviously maneuver. So these are some very fundamental challenges. So the first question that comes to our mind is that, if you ask this to any person who works with guidance laws, they would say that, how about using proportional navigation for this problem? So the classical analysis of proportional navigation has established some facts, which include that the defender speed has to be at least root 2 times of missile speed um, for interception to be guaranteed, and also that the defender lateral acceleration should be at least 3 times that of missile lateral acceleration for a guaranteed interception. So just as we start, we immediately hit a roadblock. So proportional navigation, though it's a beautiful guidance law, it doesn't really fit here because of the fact that this is an engagement between um, vehicles of equal capability. So now, moving on, I'm just trying to bring forward some notations because there is a fair bit of analysis that we will go through. I'll also give geometric interpretations. So you can see these 3 points here: the target, which is the aircraft, defender, and missile, which is attacker. So R denotes the range. So for example, R sub D is the range between defender and the target, and RDM would be the range between defender and the missile. Also, the gammas here represent uh, the direction of motion. So here it is gamma T for the target, gamma D for defender, and gamma M for missile. Lambdas are for line of sight angle. So lambda M is for the missile target line of sight, lambda D is the defender target line of sight, and lambda dm is the missile defender line of sight. You will also notice the control inputs or the lateral acceleration commands here. So the lateral acceleration as it acts normal to the velocity. So at for target, am for missile, and ad for defender. So this is just to draw the picture and see what can we do with this. All right. And there are some assumptions here. So these assumptions are essentially that these are constant speed point masses moving in a plane. The other thing that I have already pointed out, that missile and defender are assumed to be from a similar class of vehicle with their speeds higher than that of the target. In fact, very soon we will use V sub D equals to V sub M, and these speeds are significantly higher than V sub T. Now the kinematic equations, these are straightforward relations. For example, if you look at R sub M dot, then here you can see that the rate of change of this distance would depend on the component of missile velocity in this direction along the line of sight minus the component of target's velocity along this direction. So that is how you get gamma m minus lambda m and gamma t minus lambda m. So that's for the missile. Now for the defender as well, you can similarly find out the rate of change of the separation between the defender and the target. For the defender missile separation, again you can similarly put the cosine of the angle that the heading direction makes with the line of sight. Please note that for RDM we have lambda dm as the line of sight because we are talking of this these two vehicles. Now comes the line of sight rate. Again, for line of sight rate, what we need is the components of velocity normal to the line of sight. So you can just replace the cosine components with sine components, and of course you have to divide that by the instantaneous separation between the vehicles. So using that, you can find out the rate of change of the line of sight angles, the 3 line of sight angles that we are looking into. Moving on, how is it that the vehicles change their heading direction? I have already pointed that out. This is using the lateral acceleration. So gamma t dot would be at divided by Vm, and similarly, sorry, at divided by Vt. And similarly, we have the, okay, there are some small typos here, but this is essentially gamma d dot and this is gamma t dot. And gamma m dot would be Am by Vm. So here Am, Ad and At are missile, defender and target lateral acceleration respectively. And the acceleration capabilities, there is also a limit up to which these vehicles can apply their lateral acceleration. So they are all bounded. Now, so this is an extension of the classical pursuit division problem. We have seen that, but if we have to note down what are the objectives of the three vehicles involved here. So the missile's objective is obviously to intercept the target, but it should also evade from the defender. The defender has an objective of, as you can imagine, intercepting the missile, but it can also do something which can facilitate target's evasion. The target, on the other hand, has the dual objective of facilitating the missile defender interception, and also, of course, the primary objective of successfully evading the missile. And obviously, in this case, if the defender misses the missile, then the guidance problem becomes the one-on-one type where the missile pursues the target. So that's a much, much simpler situation. But we are not really looking into that. We are looking into the situation where all these three are very much involved. Now, in the rest of the discussion, I'm going to emphasize the importance of line of sight guidance as the strategy for defender, and highlight that why it works very well. You may feel that why is it that suddenly line of sight guidance is coming, why not any other guidance law? So there are some reasons why I picked line of sight guidance law for this problem when I was investigating this, and some of those geometric intuitions and explanations I will try to discuss as we move on. But for the time being, please assume that the defender is going to use line of sight guidance. What does that mean? That means that during this engagement, the defender will always be on the line joining the target and the missile. So if you see the generic representation here, I've just moved the defender from this position and put it right on the line joining the aircraft and the missile. So that is what you have. So all these line of sight angles that we wrote the kinematics about, they have all become the same angle lambda. And of course, the heading directions, they still have their different variables. And RD, RMD, RM, they are the same quantities. The only thing you can obviously see is that R sub D plus R sub MD would give you RM. So now this is the picture that we have, and let us see how do we analyze this situation and get some more results. So lambda is the angle that you have for the line joining the three vehicles as measured in a fixed frame. What exactly governs the line of sight course for the defender is the locus of all points between the target and the missile, that is RD by RM as an element of closed set 0 to 1. So that means all these positions right from here up to there. So RD is 0 here, the range defender separation from target, and RD is RM when the defender reaches missile. So with that, you have it varies between 0 to 1. It is very easy to note that at the time of launch, so of course the defender is launched by the aircraft. So at the time of launch, RD by RM is 0, and at final time, RD by RM is 1, where TF is the defender missile interception time. Please note that we are looking at this situation only up to the point where the defender intercepts the missile. So that is why we have, when we say TF, this is the interception for the defender missile pair. All right, there are a few other mathematical notations which are important for us to dive into the analysis. The velocities of three vehicles can be expressed for analytic tractability as components along and normal to the line of sight. So along the line of sight, you take the cosine components. So gamma d minus lambda, so Vd cosine of gamma d minus lambda would be the component along the line of sight. Similarly for the other three vehicles. And normal to the line of sight, of course, you take the sign components. Now the line of sight rate, it's very interesting that there are three vehicles here. And of course, if I take the line of sight joining target and defender, and then defender and missile, and then target and missile, these three lines rotate at the same rate. So the line of sight rate can be written, sorry, the line of sight rate can be written using all these three ways of expressing it. So that is between the missile and the target, defender and the target, and also the missile and the defender. The closing speeds also can be expressed using the cosine components. So Rm dot would be the component of missile's velocity along the line of sight minus the component of target's velocity along the line of sight. So that will give you Rm dot. And similarly, you can compute Rd dot and Rmd dot. All right. So moving on, the first thing that we want to establish, you might recall that in the beginning of the lecture, I pointed out that proportional navigation guidance requires a specific speed advantage while intercepting maneuvering targets. So the first thing here is to see what are the speed requirements for the defender as it moves on this line of sight course. So the main result here is that with equal speed as its adversary, that means defender and missile have same speed, the defender can keep its instantaneous position on the line of sight for all attack geometries and missile maneuvers. So let us see how that works out. Now this VD sub PLOS, we can, if you see this expressions, you can see that the components normal to the line of sight are now related through these equations. So I can use these equations. My idea here is to relate the components of these vehicles velocities normal to the line of sight, and then with that information try to derive the main result. So with these first two equations, you can readily express Vd perpendicular to line of sight, that is the defender's speed perpendicular to line of sight, as a function of the missile speed perpendicular to the line of sight and also the target speed perpendicular to the line of sight. And you can, let's see how, is there a geometric interpretation of this result? Just imagine when Rd is 0, that means Vd PLOS is equals to Vt PLOS. So how does that work? That can be seen here, that when the defender is very close to the target, then its velocity component normal to the line of sight has to be very close to that of the target for the line of sight to be rotating, to be on the line of sight. And as it moves away, that angle changes, and finally when it gets very close to the missile, then its velocity vector normal to the line of sight, because that is what is related to the line of sight rate, that should match the missile's component. That is precisely what is happening here. So as you can see, if you put Rd by Rm as 1, it will become Vm PLOS. So of course the proof is straightforward, but the idea here is very simple, that since it can vary only between these two quantities in this sort of linear fashion with respect to Rd by Rm, that means that the maximum possible requirement that the defender has as its speed normal to the line of sight is always between the set minus Vm to Vm. Now why did I write that? That is because the target is assumed to be a vehicle which is much slower than the defender and the missile, and the maximum velocity that the missile can have normal to the line of sight is its speed, so that is Vm. So the maximum requirement for Rd by Rm, of course varying between 0 to 1, would be minus Vm to Vm. And hence if the defender has a speed equal to that of the missile, it will be able to fly on a line of sight guidance course. You can also imagine that by this situation where this angle is gradually increasing as you are going away from the target towards the missile, and the exact component matching is only towards the end of this trajectory. So that is an important result. So speed wise, um, line of sight guidance is a reasonable idea. There is no problem there. Now comes another important result here, which talks about guarantee of interception. So if Rm TF is finite, so for proving these results, there is an assumption here that if the final distance between the missile and the aircraft is finite, which is obviously the case, but it is required for some of the maths, then the interception between the missile and an equal speed defender is guaranteed for all attack geometries and missile maneuvers. So let us see how we construct this proof. In this case, we have classified the engagements in two categories, where one is where the VM PLOS at any instant is greater than VT PLOS. That means the missile's velocity normal to the line of sight is greater than that of the target. So if that is the case, then I can certainly write that since VM PLOS is greater than VT PLOS and VT PLOS varies in that range, it will obviously be smaller than VM PLOS. So it will be between these two quantities. So this is smaller than that. Now I can square these terms and then add VD square or VM square. They are equal speed. And finally, we can have that. We have that VD, the defender velocity along the line of sight, the square of that is greater than the missile velocity along the line of sight. You can also directly see this, that if the vectors are of equal magnitude, so if one component is smaller, then the other one is obviously greater. So that is what is happening here. And then you only take the positive root of VDLOS, because we are not looking at the case where the defender is coming towards the target, but obviously it is moving towards the missile. So with that, if you see, now since this component is greater than this one, it is very easy to see that the separation between these two vehicles is reducing. So that means RMD dot is less than 0, and the defender closing on the missile during the phase, and RMDTF is attained. So if it is strictly decreasing, then obviously it will reduce to 0. The other case is when VMPLOS is considered to be less than or equals to VTPLOS. So in this case, we have, since this is the quantity which is greater, VDPLOS will be between these two quantities. So it is definitely smaller than this limit. And then RD dot is 0 if VDLOS is greater than VTLOS. That means the defender speed along the line of sight, if it is greater than aircraft speed along the line of sight, then obviously its separation is constantly increasing. And for that, we can obviously express this in terms of the other component, which is perpendicular to the line of sight, and the actual speed, and then just squaring here. And this, since it is already given to be less than VMPLOS, you can directly write these two things there is already a relationship here. So using that, you can see that since VD is greater than VT, and this quantity is smaller than this, just by the case here, so a bigger quantity minus a smaller quantity, that would definitely be greater than the other side. So that means RD dot increases and can attain any finite RMTF for interception. So with these two cases, what we conclude is that the interception is guaranteed if the defender follows line of sight guidance. So in some sense, you might imagine that we have got by now all the important results, and this could be, it may look like a happy ending of this quest for a guidance law. But all of you know that when you look at interception and speed requirements, that is fine. The most important consideration for a guidance law is essentially the lateral acceleration characteristics. So the for considerable time forward, I am now going to get into the analysis of lateral acceleration relations and then establish some very important results that will show that why line of sight guidance is such a good idea in this case. All right, before I do that, so for the lateral acceleration requirement, what we need is, first of all, we need to pick the line of sight rate between the missile and the target. So just as one of those relations, of course, you could have picked any of the three. You can differentiate this equation and then you will see all these terms coming up. You will start noticing Vm times gamma m dot. So that would be Am, the lateral acceleration for the missile. Similarly, Vt and gamma t would give you At. And the other part is where you have lambda dot here and then another lambda dot here, but there is a Vm cos gamma m minus lambda and Vt cos gamma t minus lambda. So that would give you another minus r lambda dot. So that that term would go to the other side, and that this whole term will become rm dot. So twice of rm dot lambda dot, and finally you can express the lambda double dot in this form. So here what you notice is that lambda double dot is a function of the missile's acceleration normal to line of sight, the target's acceleration normal to line of sight, the separation between the missile and the target, and this term which is related by the line of sight rate and the rate of change of the closing distance. So we get one expression for lambda double dot just by differentiating this basic kinematic relation. Here the I have used new notations here, AMPLOS, which is AM, the cosine gamma m minus lambda would give you the component of AM, which is normal to the line of sight, and AT PLOS again corresponds to the component of the acceleration normal to the line of sight. So by now you would notice that there are a lot of these quantities that we are always very keen on writing their components normal and along the line of sight, because this is more for the analytic tractability of this problem. So that is why in a lot of these guidance analysis we keep doing that. So this, I took one pair of line of sight relation. You can also take the other relation, for example, the missile target line of sight and also the defender target line of sight. So finally, you can express in this using this equation, you can write AMPLOS as a function of ATPLOS. Similarly, for defender, you can write it like this. So at the end of it, from the last two equations, you can substitute for lambda dot from one relation to other, and finally you can arrange these terms to obtain the lateral acceleration relationship for the defender. So this is the defender's lateral acceleration normal to line of sight as a function of target's acceleration normal to line of sight, missile's acceleration normal to line of sight, and another term which is a function of lambda dot and other quantities. Fine. So this was a bit of maths, but what do we notice here? You can see here that when your RD by RM is 0, you are just at the time of launch. So the missile's lateral acceleration does not really affect defender's lateral acceleration, because the line of sight kinematics is dictated. This is like, holding a stick from two ends. So it is the end that you're near to that sort of more affects your motion than the other end. So that could be a sort of a um, rough insight into what is happening. But as you get closer and closer to the um, missile, obviously this term then dictates. So the defender lateral acceleration component normal to the LOS is a weighted sum of target and missile lateral accelerations normal to the LOS added to a component proportional to the LOS rate. This is an important result which is used further for proving strategy advantage and deriving a cooperative guidance law for the aircraft. All right. Moving on, I do have some more mathematical results, but in the interest of time, what I will do is that I will just give you the gist of the couple of theorems that are coming. And then we will focus more time on the geometric aspect so that we have a good feel for why this particular guidance law works here, and then we'll move on from there. So so this section is decisive lateral acceleration advantage. So we have got an expression for lateral acceleration, but still we don't know much because we don't know how this expression relates to, for example, if I know how much is target's acceleration normal to line of sight, can I get a bound for my defender's lateral acceleration normal to the line of sight and things like that. So the assumptions for the next theorem is that assuming a non-cooperative aircraft, by that I mean that the aircraft is not maneuvering and the missile is using proportional navigation guidance. Now, why is that a reasonable choice? You can assume that the incoming missile, which is intercepting the aircraft, is using something conventional because its engagement itself in some sense conventional. Assuming that it doesn't know that there is a defender launched, proportional navigation would be an excellent choice for the red missile to intercept the aircraft. So if you assume that, and if you also assume that Vm and Vd are both greater than 2 times Vt, that means missile and defender are moving at speeds which is greater than twice of that of the aircraft, we can eventually prove that the lateral acceleration of the defender at the end as divided by the lateral acceleration of the missile is going to be between -1/3 and 1/3. Okay, so before I comment on that, I'll just give you the gist how you do that. How you're going to do that is that you have this relationship AD PLOS and the other terms. You can take AM PLOS to the other side, divided by that, and then also the AM PLOS itself can be replaced by proportional navigation, which is the choice of guidance law for the missile, which is -3 Vm lambda dot. The minus is just because of the frame, the reference that we have taken. So if you do that, you will immediately get this equation, which is at the bottom of this slide. So this is now set up, but beyond this, there are certain conditions. You can take the partial derivative with respect to Rd by Rm, and you can deduce that with respect to Rd by Rm, this quantity is always increasing. If this quantity is always increasing, then we can substitute Rd by Rm as 1 in the expression and then find out the limit. For example, in this case, if you put Rd by Rm equals to 1, finding the maximum value, and you assume that the closing speed between the defender and missile is positive, which is a reasonable assumption, the ratio is less than 1. But moving on, you can also see that if you look at the minimum value, that would be at Rm by Rd equals to 0, which is a slightly simpler expression, as you see here, because this would become 0 and then this would also become 0. and you can get this result which goes by that. But then you can again look at the maximum value that you got and get the bounds just by using the kinematic relations that we already have. So what we can show by these relations is that ADPLOS by AMPLOS lies between minus 1 by 3 and 1. And then moving on, if you look at this slide here, this quantity we assume that this is greater than 0. That means the defender and missile are closing at a positive using a positive closing speed, but it can actually, this is typically much more than that. So if you put that information also in here, in that case what you can show is that minus ADPLOS by AMPLOS at the final time is indeed between minus 1 by 3 to 1 by 3. We do have more information on this result. The maths part is here. I also have a reference at the end of the talk, so you can also have a look at it. But I would like to emphasize here is that proportional navigation, for example, in this intercepting a maneuvering target would have an acceleration which would be 3 times that of the missile, and here it is 1/3 of that. So this is a tremendous result in terms of the problem that we are trying to address. Then there is another theorem here which is very straightforward, which says that the if the missile on a collision course with the target, it pays maximum penalty for an evasive maneuver from the defender if the defender uses line of sight guidance. So here you can just imagine that this missile and target are already on collision course, this VM and BT, and now the missile can sense the defender coming in. So it uses an evasive maneuver which is normal to its line of sight between defender and the missile, which is AME. Now its component which is normal to the line of sight between target and missile, that would be a penalty because it will make the missile go away from this collision triangle which it had established with the target. And you can very easily see that if this angle is 0, then the AME and AMP will become equal. That means any evasive maneuvers that you are taking to avoid the defender would directly give you the maximum penalty with respect to an originally established collision course. So the proof is also very simple, again based on the same thing. So the distance traveled normal to line of sight. So whatever deviations, whatever penalty you pay is assumed to be governed by AMP, and AME and AMP will become equal if this angle is 0. That will happen when the defender is right on the line joining the two. So we can see geometrically why line of sight guidance is also an intelligent option, since it will now make the missile pay a heavy penalty if it is trying to evade from the defender. Okay, so the maths part, some of it we have done fairly rigorously, some of it we have only seen the gist, but what I would really like to discuss with all of you is this picture where we can see why line of sight guidance gives these tremendous results here. Now, just imagine that this is the situation between missile and the target. The missile, of course, would like to close this gap because the missile's aim is to achieve a collision course with respect to the target. So this missile will now turn towards this direction, anti-clockwise direction. Now, if the defender is using line of sight guidance, the beauty of it is here that it never tries to close its collision triangle with respect to the incoming missile, because its heading is governed by the line of sight guidance principle, which says that hold on until you get too close to the missile. For example, if the defender was very close to the target, then its velocity component normal to the line of sight will only be equal to that of the target. So it is not immediately going for the interception, but rather waiting for the missile, and the missile is anyway turning towards the target, so it is already closing this collision triangle with respect to the defender. So this is something inherent, not that we have put extra logic here, but this is an insight that why line of sight guidance works so well here. Now imagine if the defender was using proportional navigation, it would immediately close this gap between alpha and beta to achieve the collision course with missile, but the missile is maneuvering and it will immediately change its heading to close the heading error with respect to target, because it wants to be on that collision triangle. So it will be chasing that situation. But here it's beautiful, because whatever effort the missile is doing is only helping the defender, and the defender is just keeping the line of sight course, and it will only close alpha equals to beta when it gets very close to the missile. So these are lower heading angles from the line of sight, so the lateral acceleration is lower. And the bigger point is that it inherently takes the advantage of the enemy homing maneuvers. So this is a geometric insight to why line of sight guidance works so well here. All right. As far as implementation is concerned in any engineering system, the ideal kinematics, if you want to implement, you need some controllers, tracking controllers. So again, for this line of sight guidance for defender, you will have to add a compensator which can give you a more realistic sort of tracking logic. But this is just for that. There is also another result that I wanted to discuss is with respect to the cooperation between these two vehicles. That is the blue team, the aircraft and the defender missile. The premise to this analysis is that the aircraft is now going to use a negative quantity times the line of sight rate, because it is trying to evade from the missile. So this is the cooperative maneuver that the aircraft wants to use. Now this cooperative maneuver will induce maneuvers on the missile, and that will obviously induce more acceleration on the defender. So what exactly is the idea? So the idea here is that the aircraft should maneuver so that it evades from the missile, and now the missile will have to maneuver more, so it will bleed energy. At the same time, it is important that this cooperation is sensitive to the fact that the ratio of ADPLOS and AMPLOS is still kept less than 1. So that is the premise for this analysis. Again, it's a straightforward analysis. You can just use the same relation between ADPLOS and AMPLOS and plug these values. ATPLOS now has a closed form which can be substituted here. And what we are going to do is maximize mu while keeping ADPLOS to be less than 1, ADPLOS by AMPLOS. So hence we solve for mu, and then again this kinematic relations can be easily reduced. Here you have another quantity, but since Rm itself, Rm dot is a negative quantity, so for the minimum we can certainly put that bound. And 1 minus Rd by Rm, again this if this becomes close to 1, this would be a very high quantity, but if it is close to 0, we can get the lower bound. So we get 2 Rd dot plus eta, which is the navigation gain that the red missile is using, which is a positive quantity. So finally, we can come up with a mu, which is 2 Rd dot, which is coming from this optimization, and then that is used as the cooperative guidance law by the aircraft. So towards the end of this discussion, what I have now is some simulation which go by the analysis we have done. And I would just like to show that here there is a 5-kilometer distance between the vehicle. So you see here, this is the 00 is the initial position for the aircraft. And then here is the missile's initial position, that is 20 kilometers. Okay, I think there is some typing error here. and the missile is obviously using proportional navigation, so it is on this kind of trajectory intercepting the aircraft. But the target aircraft launches the Defender, and I have also shown the comparative trajectory for PN, although our focus is obviously on the Defender. And these are the initial heading directions. You can note that this odd looking figure for the Defender, that is because it is the line of sight, maintaining the line of sight course, there is a specific initial angle, so it uses that. These are the lateral accelerations. First, I would like to show you the blue curve, which is the CLOS, or command to line of sight, or line of sight guidance. You can see that it varies smoothly to a very small value. However, if the missile would have used proportional navigation, then the lateral acceleration would have been way higher. With n equals to 5, of course, the initial acceleration is high, but it is able to manage. But if you just use proportional navigation with n equals to 3, the latex actually saturates around 20 G. But the line of sight guidance gives way superior performance here. This is that AD by AM that I wanted to show, that the analysis that we did, you can see here that for line of sight guidance, command to line of sight guidance, AD by AM indeed gets very close to 0.33. This is the bound that we had deduced. And you can imagine how bad the situation is if you use proportional navigation, because that is now close to -5 or -4 times. So this is just the other results I have are very straightforward results, where you see the capture regions for these, because there are various different attack geometries that can be considered. So for a side-on attack geometry, which is essentially this, here the missile can come from any angle between say 90 degree to 270 degrees. So all that is done here, and you can see that the miss distance is 0 for PNG and with n equals to 5 and line of sight guidance. PN with n equals to 3 doesn't work that well. But the control effort, which is the integral of AD square dt, that is minimum for the line of sight guidance. That trend continues. Of course, there is relative difference, because head-on geometries are a little difficult because the closing speeds are higher, so the capture regions shrink. But for line of sight guidance, it still works well. Total control effort also, line of sight guidance gives you a little lower. I mean significantly lower as compared to the other two. Then similarly for the tail chase, again the control effort is minimum for line of sight guidance. This is a simulation that I have which highlights the cooperation between the vehicles. So what the aircraft does here, it is the similar situation that we had towards at some point in the engagement, it starts this evasive maneuver, and then you can see that this is the missile coming in, and because of this maneuver, this missile now turns more steeply towards its left, and that actually in some sense helps the interception between Defender and the missile. So this is the missile lateral acceleration. Once the cooperation starts, the aircraft maneuvers, it also has the acceleration of the missile increases. However, for the Defender lateral acceleration, of course, it also increases, but it is noteworthy that it is the ratio that is still, it tries to maintain below 1. So that is the idea of that optimization. So this is how this looks like. This is aircraft's maneuver. So that is just after a certain time, it takes this maneuver. If you see the effect of cooperation on the integral ratio of integral control effort, then you can see that when you have cooperation, you gain a lot in terms of AM square dt integral divided by AD square dt. And please note that for aerial engagements, energy bleeding is a fundamental consideration, and hence if this ratio is high, then the incoming missile is losing the advantage very fast. Similarly, for the other attack geometries, we can see the advantage is still very much there. All right, so I would just like to conclude here and maybe have take some questions that would be more worthwhile. So what we have looked at is line of sight guidance as a prospective guidance law in the 3 vehicle engagement scenario. And we have seen that it gives you a lot of speed and lateral acceleration advantage even when the aircraft is not maneuvering, but if it cooperates, you get even better results. We looked at very quickly the 3 standard attack geometries: side on, head on, and tail chase. And the both by analysis and simulation, we have shown the advantage. And the aircraft considerably increases the missile to defender total control effort by using the cooperative guidance law. Okay, so I would like to thank, yes, of course, Professor Talshima, my collaborator. So I did this for quite some time back when I was in my postdoc, and it was supported by Air Force Office of Scientific Research. And this is the article that some of this analysis, although most of it I have tried to cover, but some of it I couldn't go into in great detail because of the time limitation. So that can be seen here. So I think we'll now stop for questions. I'll stop for questions and I'll look forward to hearing from all of you.